In this video, we will talk about point charges and electric fields. We will define point charges and introduce the units with which we measure their strengths. We will also introduce the two possible signs point charges can assume. Next, we will talk about the electric fields these point charges produce. And finally, we will do some calculations and solve problems based on these concepts. A point charge can be sketched in the following manner, and it comes with two possible signs. So a point charge can have a positive sign, a positive charge that is, and it can have a negative charge. Note, this is a point charge, so they have no dimensions, meaning the radius is 0. I am just exaggerating the scales in these sketches. We can use symbol Q to denote a point charge, for example, Q1, and this is a Q2, and so on and so forth. And we can measure the strengths of these charges in a units of coulombs. So coulomb is the SI unit to measure the strength of a charge, electric charge. Abbreviation is capital C. We also add Q, electric charge, is a scalar quantity. So although they come with positive and a negative sign, they don't have any directions, they just have magnitude, and therefore they are scalar quantities. Example of a negative charge is an electron. The symbol to denote is E. The charge the electron carries is minus 1.602 times 10 to the power minus 19 coulomb. An example of a positive charge is proton, and the charge it carries is plus 1.602 times 10 to the power minus 19 coulomb. So you see the magnitude of that charge of an electron and proton are the same. The only difference is in the sign of the corresponding charges. This value, 1.602 times 10 to the power minus 19, is a natural unit of charge. So every amount of observable electric charge is a multiple of this basic unit. There are some important points that we need to understand regarding charges. The first one is like charges repel. So if you have, let's say, two positive charges like that, they will repel each other and move in an opposite direction. Same thing happens when you have two negative charges. So like charges repel. The second point is opposite charges attract each other. So if you have a plus charge and a negative charge, what they're going to do, they will attract each other like that. The reason for these behaviors will become clear soon when we discuss electric fields. Point number 3 is conservation of charge, meaning the algebraic sum of all the electric charges in a closed system is constant. To understand this, let's assume initially we have fur and a plastic rod. Both are initially neutral, meaning the number of positive charges and negative charges inside of them are identical. So they are neutral objects. So the net charge of this closed system that consists of fur and plastic rod is 0. Next, let's rub the plastic rod with this fur. Now in that process, what happens is that a negative charge from that fur will get transferred into the plastic rod. So the plastic rod gains a negative charge. So now you see the fur has a net charge of plus 1, and the plastic rod has a net charge of negative 1. However, the net charge of this closed system that consists of fur and plastic is still 0 coulomb. So in this charging process, what we have done is just to transfer charge from one object to another. We did not create or destroy any charge. So this is the essence of conservation of charge. Charges cannot be created or destroyed, but it can be transferred. However, the algebraic sum of all the electric charges in any closed system is constant. An important property of electric charge or a point electric charge is that it creates electric fields. It is a source for electric fields. So a positive point charge can create electric field in a perfectly radial manner. So the arrows are representing the electric fields that this positive point charge creates. The red arrows are the electric fields due to this charge. As you can see, this electric field is a vector, and it can be quantified in the units of newtons per coulomb, that is the SI unit, to quantify electric fields. An important property of this electric fields created by this positive charge is that the direction of this electric field is radially outward meaning away from that source, from that point charge. Likewise, for a negative point charge, the electric fields it creates, it will be in a direction towards the negative charge, as shown. It's also radial, but the direction now towards the negative charge. Of course, this is a three-dimensional pattern. It extends in a three-dimensional space that we have sketched on a two-dimensional plane. Another thing that we have to understand is that it has a very nice spherical symmetry to it. Now, what that means is, if I have say a positive charge, the magnitude of this electric field everywhere at the same distance from the source, let's call that distance r, is the same. So the magnitude here, if let's say is 2 newtons per coulomb, then the magnitude there will also be 2 newtons per coulomb, 2 newtons per coulomb, 2 newtons per coulomb, and so on and so forth, as long as the value of r is the same for this point, for that point, for that point, and for that point, meaning all these points are at the same distance from the point charge. The only thing that will be different is that the direction of the electric field. So at this point, the direction of the electric field will go upward. At this point, the direction of the electric field will go rightward. For this point, it's going to go like that. For that point, it's going to go like that, and so on and so forth. Notice that we have maintained the outward direction for the electric fields because we are talking about positive charge. So if this point charge has a strength Q coulomb, the electric field at distance r from that point charge has the following mathematical form. K, the strength of the charge, over the distance squared. Now this K is a constant with a value of 9 times 10 to the power 9, with a unit of Newton meter squared over coulomb squared. That is the unit for that constant K. So we will be using this equation to calculate the electric field due to a point charge soon. So let's assume you have a point charge here. The strength of that is 4 nanocoulomb. You want to determine the electric field, the magnitude of the electric field it creates at point P, a distance 30 centimeters away. So according to the equation that we have just written down a few minutes ago, the electric field at a distance r from the point charge is given by that constant K, the strength of that charge in coulomb, over the square of the distance from the point charge to the point of observation. So in this case, K is of course a constant, so 9 times 10 to the power 9. Q is a 4 nanocoulomb, so 4 times 10 to the power minus 9. You have to change that into coulomb. The distance is 0.3 cm, so if you change that into meter, that's going to be 0.3 meter, and do not forget to square it. And that's going to give you 400 newtons per coulomb. Another example, you have two charges. One is 1 coulomb at x equals to 2 meters, and minus 1 coulomb at x equals to 4 meters. What is the electric field these two charges create at x equals to 3 meters? Let's do one by one. Let's look at the 1 coulomb charge first. This is a positive charge, so the electric field at x equals to 3 will be heading in that direction. Remember, outward from the positive charge. So the electric field that this charge creates at that point will be in the direction of I hat, or rightward direction. So the magnitude will be K, Q is 1. The distance between x equals to 2 and x equals to 3 is 1. So that is 1 squared. Do not forget the direction, I hat. Now let's look at the negative charge. This is a negative charge. So the direction of the electric field that this charge creates at that point will be going towards the negative charge, which means also in the rightward direction. So it would also have the direction I hat. So the magnitude is again K. It is 1 coulomb. The distance between x equals to 3 and x equals to 4 is 1, so 1 squared I hat. Note, I do not put a -1 here. The reason is the effect of that -1 coulomb is contained in that direction of the electric field due to that minus charge, which is also I hat. So you just have to sum the two terms, and that's going to give you 2k I hat Newton per coulomb, which is 1.8 times 10 to the power 10 I hat newtons per coulomb. So the net electric field due to these two charges at that point is in that direction. Next, we want to explain why two like charges repel. So let's say you have one charge, positive Q, and another charge, positive little q. This capital Q produces an electric field of E subscript capital Q in an outward direction from it, like that. So if you place a positive charge right there in the path of that electric field, this little q will experience a force given by the following equation. So this is a vector equation that says the force exerted on this charge equals the strength of that charge times the electric field created by the other charge. So this is a positive charge. The direction of that electric field is in I hat direction. So that means the force experienced by this positive charge must also be in positive I hat direction. That would cause this charge to move exactly like that, away from this charge, causing it to repel each other. If I place a negative charge there, the force on this negative charge is also given by the same equation, Q times the electric field produced by that charge. However, this little q is negative, and this electric field is in the direction of positive I hat. So negative times I hat is minus I hat. So the force on this little q will go in that direction, opposing the electric field in a rightward direction. So we view that as attraction, as if this is attracted to that. To summarize, if you have electric field as shown and you have a positive charge like that, this positive charge will move in the same direction as the direction of the electric field. So we call it repulsion. If you have a negative charge, this negative charge would move in that direction, opposite to the direction of the electric field. We call it attraction. Let's look at the following problem. At what distance from a particle with charge 4 nanocoulomb does electric field of that charge have a magnitude of 5 newtons per coulomb? So what is R? So in this example, we are just interested in the magnitude. Magnitude at point R, or distance R from the point charge, is given by K Q over R squared. Now, since the value of the electric field at that point is 5, note it's an SI unit, equals K is 9 times 10 to the power 9. The amount of charge is 4 nanocoulomb, so if you change that into coulomb, over R squared. And you can solve for the value of R, which is 36 over 5 square root, and that is 2.68 meters. So that is the distance for which the electric field has this magnitude from a charge with this much strength. Thanks for watching.